Okay, the room is quiet, and they tell me that the mic is working, so we'll go. Hello, everybody. First of all, I will say that I'm Mike Witherell. I'm the laboratory director of this great laboratory, and it's a great privilege to be leading what is, I think, a unique laboratory and the breadth of science and technology it's able to do research on. This is the second event in our Women in Science Speaker Series. This is something we developed about a year ago as an idea. It's part of our Diversity, Equity, and Inclusion lab-wide initiative and designed to bring women with extraordinary accomplishments in science to talk to our community. We don't have an agenda about what that conversation is. It, I think, naturally comes out quite well, and we just get these really remarkable and accomplished women to come in and talk to us. So, in that light, I would like to welcome Geri Richmond to the laboratory. She's the Presidential Chair in Science and Professor of Chemistry at the University of Oregon. As we were saying, she began her academic career at Bryn Mawr College and later moved to the University of Oregon. And she has focused much of her research work on measuring the hydrogen bonding characteristics of water surfaces in contact with a variety of media. She's made discoveries of how molecules behave at air, water, and oil-water surfaces. And she is one of the world's foremost contributors to our current understanding of the chemical processes that occur at water surfaces. Her professional organization, the American Chemical Society, gave her the Priestley Medal just this year. And as a colleague said at the time of that award, results from her laboratory are instrumental in understanding everything from corrosion science to atmospheric chemistry. She's also been awarded the National Medal of Science, the Joel Henry Hildebrand Award, and the Theoretical and Experimental Chemistry of Liquids, the Davison-Germer Prize in Surface Physics, an amazingly broad range of awards for her work. She is also a devoted and tireless advocate for women in science and has been a real trailblazer in assuring a diverse workforce. She is the founding and current director of COACH, which is a grassroots organization formed 20 years ago to help women in science and engineering careers. Geri has said that with COACH, we have a motto to be relentlessly pleasant. So we are relentless and we are pleasant. I can add to that, she is also pleasantly relentless, which is a different thing. And that is what science needs right now. 20 years on, COACH has helped to advance the careers of over 20,000 women scientists and engineers in the US and in developing countries around the world. In addition to all that, Geri has been a leader in the national and international scientific communities, past president of the American Association for the Advancement of Science, which is the largest scientific organization in the country. She's on the National Science Board, which is the governing board for the National Science Foundation. Finally, she is secretary and member of the board of directors of the American Academy of Arts and Sciences. So I had the privilege of being inducted to the American Academy a year ago, and Geri was responsible for announcing all the new physical scientists. So she started out by waking up the audience with an enthusiastic, "Let's hear it for the mathematical and physical sciences." And so our group all led a cheer. And then John Lithgow, the superb and well-known actor, was also on the board, and he followed up with, "We can't let them outdo us. Let's hear it for arts and humanities." And so all this meant that for the rest of this group, it was more like a high school graduation environment than a award ceremony. So she properly disrupted the environment there. So I'd also, before we bring them up, I'd also like to give a warm welcome to NPR science correspondent Joe Palca. He helped us to lead the conversation for our first Women in Science Speaker Series event, Jennifer Doudna, which I thought went extraordinarily well, and we're pleased that we were able to bring him back for this. He's well known for his insightful reporting on science and technology, one of that very small group of journalists who still are dedicated to covering what we do. He began his journalism career in television, turned to print, and he went on to NPR, where we all hear him regularly. Joe's interest in telling stories, not just about scientific discoveries, but about the process, led to his program, Joe's Big Idea, exploring how ideas become innovations and inventions. And this has actually gotten a very broad coverage around the country. I will say that in addition, Joe has a feel for the people who do science and technology, and that's an important part of telling the story too. He received his degree from Pomona College, got a PhD in psychology from the University of California, Santa Cruz, and we just heard was recently given a very distinguished award from Dartmouth Engineering School, actually, for work that he's done. So he's broadening his impact. So please join me in welcoming Joe and Geri to Berkeley Lab.
We're really in trouble because, you know, that first one went so well that it's only downhill from here.
That's right.
So,
That's right.
You know, lower your expectations and you'll have a great time. No, this is a great honor for me, and really, you know, these are, as you heard, it's a little open-ended what these conversations are about. Are we going to have questions from the audience? I saw there was a microphone. Okay, so at some point we'll do that. So thanks. You know, as I was indulging in a little social media watching before this event, I looked to see that the lab put up, you know, this was being announced, and somebody put up a response to Women in Science. And I don't know if this was a troll or whether he was making, or she, or whoever it was making a serious comment, but he said, "What about men in science?" And I thought, well, you know, I've done that for the last 30 years. But it made me wonder if there's a deeper question there about why this lab, why various places feel the need to talk about women in science, and what's the goal of doing that? What would you like that to accomplish? So I thought I'd start there.
Well, that was a softball question. Well, first of all, it's great to be here. Thanks for asking, and thanks for all of you that are here. So my answer to that is that we know that the best science is done when you have diverse voices, you have diverse expertise, you have diverse experiences in the room solving a scientific problem. And we're not so good at that in terms of the populations that are doing science now, in terms of diversity. And so I think it is important that we all work hard to make certain that as many voices and people are at that lab bench or at that table to come up with solutions for the difficult problems that we have. And so if we're underrepresented in any group, I think it's important for us to note that and to work for solutions.
But okay, but let me push back. I mean, there was quite a bit of science done 50 years ago or 100 years ago where women and other people were definitely underrepresented, and they still managed to accomplish something. So is it your argument that we would have gotten further faster if we...
Yes, absolutely. Okay. We would have been on the moon maybe 1900.
That's interesting. I mean, I wonder, so how would you measure that? I mean, yes, if we were on the moon, we can't go back and do the experiment, but how will you know that impact is what's socially responsible, viable? I get it, but how will you know when you've succeeded?
Boy, another softball question, huh? I don't know that we have metrics in place to be able to do that.
Yeah.
But I do know that the richer the conversation is, the richer the solution solving is, when you have people that may not be so comfortable with each other. And so that's why that's really why we need to make certain that we have everyone at the table. Because when we're all comfortable with each other coming up with a solution, we come up with the same solution over and over.
Yeah, it's true over and over, and it's very hard to make people grapple with that. Do you find? Because a lot of, especially in science, I find that people are very reluctant to say that they have a bias that might be affecting their judgment, whether it's against male, female, black, white, whatever. It's very, because supposedly there are no, I mean, those distinctions should disappear because the data are the data.
Right.
But they're still there. So how do you explain to somebody who says, well, I know we should have diversity, but we only found good male candidates for this position?
How do you convince them that they...
What do you say to somebody who says that to you?
Are you sure you had all the best talent in front of you?
Right.
Are you sure you had all the best talent? That's what I would respond with. Tell me how you're sure you had all the best talent if there were only males in front of you.
Because I face this question now where I've looked at the percentage of women versus men that I interview over the years. And I've specifically looked in the last 5 years, and I think my best year was 38% or 37% women. But if you go to the Lawrence Berkeley Lab press office or a lot of university press offices and they announce something, a lot of times it'll be the PI that you are introduced to, and the PI tends to still be a man. Mm-hmm. So what's my role in terms of saying, well, I know I could talk to the PI, but I'd rather talk to the grad student who actually did the work? What do you think about that?
Well, I think that's great, but I always think it's important for us to give more credit to the grad students because they're doing all the work.
So so wait a minute. So what's wrong with you?
What's wrong with me?
Didn't you get fully indoctrinated in, no, never mind. Okay. All right, so enough of the hardball questions. Let's go back to the softball. When you were at Bryn Mawr when? I'm just curious.
80 to 85.
80 to 85.
On the faculty. First female tenure-track faculty member at Bryn Mawr Women's College.
That's right, it was faculty. Because I was going to say I was at Swarthmore, but before you were on the faculty there. But you didn't go there as an undergraduate.
No, I went to Kansas State.
Okay, so so what was it at Kansas State that started you on the path that you're on today?
Oh, it's undergraduate research. There's no question.
Okay.
There's no question.
What did you do?
Oh, my gosh. Do you really want to know?
I think people came here because, they want to hear about that stuff. I could be wrong. Maybe they want to hear.
So I originally was going to be a math major. My mom was a beautician. My dad was a farmer. So I had no idea what science was at all. No idea. But my mom always said, be good at math because that'll take you places. And so I went to college and I majored in math. And I was working my way through college, so I was working retail. I was actually selling wigs to men. But we won't go that further. Anyway, it was the 60s, and the guys wanted to have long hair, but they couldn't because they were in the Army. Anyway, so I was doing this job on the side, and so I was also taking chemistry, and the chemistry professor noticed me in the sophomore year, and he said, you just aced this analytical chemistry exam, and who are you? Mm-hmm. And I said, well, I'm a math major, and he said, well, smart students like you, we'd love to have you, need a job? We'd love to have you working in the chemistry department doing things. So I said, a job? Sounds great. And so he said, well, you have to it's good if you're a chemistry major if you take this job. So I switched and became a chem major. And part of that then, in terms of what turned me on to science and chemistry, was that I worked in a guy's lab. His name's Cliff Malone. And he had the coolest projects going on. And remember, this is Kansas, okay? So the project he was working on was to take, now this may be after lunch, not so good. He wanted to have insecticides to kill bugs in the farm field, but he didn't want to have to spray crops. So his idea was to make plastic cow pies. We know what cow pies are. We do not eat them. Plastic cow pies and put them in the field, and then you put the insecticide on the cow pies that would attract the flies, and then once they land on the artificial cow pies, they would die. Okay? So what do you have to do to get flies to come to an artificial cow pie? You have to find out what the chemical is for the smell of regular cow pies. And so in his laboratory, he had all these blenders. chewing up cow pies, real cow pies, and then extracting the smell. And I thought, wow, this is pretty cool. And, and he did isolate it, and he got a patent on it. But the other thing he had going on in his laboratory was he was convinced that every mother in this country would want to send their child off to camp with snake repellent. Right? And so he was into then finding a snake repellent. And so that meant having snakes around the lab in cages in order to figure out what snakes don't like. Now, would this like heaven on earth in terms of undergraduate research?
Oh, yeah, I don't think anybody would doubt that coming into the lab every day and extracting the perfume of a cow pie, that's why sometimes I have a hard time explaining why scientists like their work to the public. But, okay, it's funny that you say it's so cool because it is so cool, but can you go a little deeper? I mean, why was it? Because with your background of coming not from a science background, not necessarily being taught to appreciate the natural world or the mysteries of the world, how did that come to be? How did that mystery come to you as being important?
Well, it was entertaining at first to be in Cliff's lab. But then I started taking chemistry courses, and I took, for those older people in the audience, organic chemistry was taught out of Morrison and Boyd, little green book, okay?
I had that.
Yeah, I swear to God, I loved Morrison and Boyd. I could sleep with it at night. I loved learning organic chemistry and just visualizing everything. And it's the first time I ever thought of writing to authors and saying how much I loved their novel, only it wasn't a novel, it was the organic chemistry text. And then I took physics, and that just sucked me in even deeper. And so I just fell in love with the science, and I couldn't imagine doing anything else. I mean, I did it 24/7. I just got sucked into it, and the intellectual challenges, and it was like solving puzzles all day long. And then I started doing research in an organic chemistry laboratory, and then I moved on to a physical chemistry laboratory. And so I worked in 3 different undergraduate labs. And then I worked here at Berkeley for a summer in undergraduate research. I worked at Vermont for a summer at IBM. I mean, I never gotten on an airplane before till I flew to Vermont. I mean, It was just, this whole world opened up that just completely changed my life.
So did you perceive a bias against women in those days? Or was it not obvious to you that that existed?
Well, Joe, that's a really good question. Something happened to me when I was in my junior year in college. And that was I really wanted to work in a particular professor's laboratory, and I was acing his course. But he wouldn't let me work in his laboratory, and so one of the other professors in the department said to me, "Geri, it's not about you. He doesn't let girls work in his lab." And I was really taken back by that, and it happened almost coincidentally with a course that I had enrolled in. And the course, so as a science major, I just wanted to do science. I didn't want to do this humanities and social science stuff. So I was going through the catalog to figure out what course I could take that would keep my interest that, was in this philosophy or something. And I found this course called Sex and Politics. So I thought, sex and politics, that might keep my interest, 20. But it turned out to be an early feminism course. Feminism did make it to Kansas by 1974. And it was an eye-opener because in that we had discussions about how there can be biases against women in male-dominated fields. And I thought, male-dominated fields, gee, let's see, there were 4 of us in my calculus class of 300 or 400. I guess it is kind of male-dominated. And it was just an eye-opener. And then I said, oh my God, it's not me. It's other people biases. So that was really the eye-opener. And it was really when I started working on women in science issues, that early. And because I wanted to see us all at the table. But it was really an eye-opener for me. I just, suddenly things fell into place and I figured it out, and then we went off to graduate school and here at Berkeley, and there were some challenges there. But
Yeah, so, okay. But you never did get into this person's lab at
No.
Kansas. And what about here at Berkeley? You said there were some challenges.
Well, there were challenges because we're so small in number in chemistry. I think there were 12 or 13 of us out of 50-some graduate students in the incoming class. But I felt my research director, who was George Pimentel, was very welcoming. And so the challenges were more just dealing with other people around, but in terms of my advisor, I always felt he was very supportive.
I was reading about George Pimentel and your relationship to him, and at least in Chemical and Engineering News, they talked about that you found his hands-off, letting you find your own way. Did you ever feel lost in that? I mean, sometimes you need to be guided in a graduate experience, and I got a little lost in mine, but maybe you didn't in yours.
Oh, I think as a graduate student, graduate school is part of the motivation behind graduate school is to lower your confidence level as low as it can possibly go. So lost goes with the program. But I think you also work through it. I had taken off 6 months before I went to graduate school to just hitchhike around Europe by myself, and I got a lot of confidence in my abilities to manage myself and manage my time. But there were times when it was hard, but God, I couldn't have been happier. I mean, I learned how to use the machine shop, and I was building this laser, and I had these capacitors, like 3 foot tall, and they discharge in a few microseconds, and they put out this big blast, and there are chemicals that exploded, and there are a lot of other things to worry about in that research project other than discrimination. It was like a lot of other things going on. But I also have to say, here in the audience with me is this husband, Steve Cavan, who's been with me since the first day of graduate school. And he's looking up, rolling his eyes. But it was wonderful to have him as a support system, too.
Yeah, it does make me feel that the women in science is almost a societal thing that has to be everybody in science at some level. I mean, men have to be part of the change,
yes,
or it's not going to work
yes,
very effectively.
that's right.
Anyway, so you got your PhD, you went to Bryn Mawr and taught for a while.
And had research going on there, too.
And had research. So what was your research originally?
Well, it started out by looking at, because I was in graduate school, I built this chemical laser, and that was in the early days of lasers. And so I was very excited about seeing what I could do with lasers. And so when I went to Bryn Mawr, then I got enough money to put together a dye laser and be able to study. First of all, studied some work with biological systems, metal binding to protein systems. But then got very interested in being able to study the surface, electrochemical processes, the study of metal surfaces using laser systems.
So I guess I'm going to allow myself to be dumb for a second because I'm good at that, and ask what a chemical laser is.
Ah, thank you for asking the question. So these days, most people that use lasers are used to thinking about shooting a light beam at something off the laser, add a chemical to make the chemical do something or change its structure. In this case, a chemical laser is one in which the chemistry goes on inside the laser, and then it puts out a certain kind of light. And so in this case, what I was producing was very excited HF molecules, which then lased. So then the light that they gave off then would bounce off one mirror and the other mirror, and then I would be detecting the color of the light that came off it to understand the kind of excitement that was happening with this HF molecule once I blasted it with, well, actually I made it from CLF and H2. Put them together, flashed it, made HF, then looked at the light that came off of the HF.
And what determines, I mean, I always wonder, why HF? I mean, why not HCl or something like that?
Well, it could have been done with HCl too. In fact, there's chemical lasers with HCl. But these particular systems allowed you to create, for any kind of a laser, you've got to create some type of what we call a population inversion, more stuff up than down, so that when it comes down, it'll create light that you can see. And in this case, these HF does produce this inversion, but in very obscure states that then I could watch with this, the light that came off.
See, I like the fact that we've just traveled into a sphere where I have no idea exactly what we were just talking about.
I really tried.
I mean, I know it's there. I know something's up and something's down, and there are levels and shells and electrons going in various places. But this is what happens. It's very weird when you're trying to describe to the public or people
Right.
what you're doing, and you suddenly realize you have to scale back so far.
Yes. But see, I've got a mostly scientific audience.
Right.
here.
So does everybody? Okay. So we have a room. Does everybody know already a priori what a chemical laser is?
Oh, they're so old. Nope. And yeah, only old people are going like this.
All right. I'm just saying. But I just hope everybody noticed that I got two elements in the right part of the periodic table, fluorine and chlorine, which I knew were sort of somewhere in there. Okay, so you built that laser at Bryn Mawr.
No, I built that laser at, I built the dye laser at, I didn't take the chemical laser to Bryn Mawr, God forbid. I didn't want to do gas phase stuff that exploded anymore.
Of course not.
So I went to Bryn Mawr and went into the safe zone in a dye laser and studying biological systems, and then also going on to study the surface of metals to try to understand how water interacts and is involved in corrosion on metal surfaces.
So okay, that's great. I mean, that's one of those things that people don't think about it. What is happening? What is corrosion? Mm-hmm. How do you define corrosion? I mean, I think everybody, oh, corrosion, sure. But what is corrosion if you have to lay it out specifically?
So in chemical terms, I would consider it to be oxidation of the metal, so tarnishing, you can think of.
And is water exclusively involved in that, or can you get to corrosion without water?
Well, you usually have water and air and sort of normal atmospheric conditions, but you also have ions make a difference too, so having some salt around with some water. And so the idea was to be able to understand the initial processes of metals starting to break down when next to salty water solutions.
So at some point, what is it? Okay, I'm going to dig a little. What does it mean for a metal to break down?
Oh, for the surface of the metal to react with its environment.
Right. And why would it not do that, or why do some metals react more vigorously than others with their environment?
Well, just by basically how reactive they are, how willing they are to give up their electrons to play with something in its environment. I'm trying, Joe.
No, I'm getting it. I'm just loving these fundamental properties of matter. How willing chemicals, how willing metals are to give up their electrons and play with others. It's such a interesting. It's such a way of looking at the world that I think. Well, I mean, it's helpful. You were saying it was like a language, and I think that's a very interesting analogy about. Can you talk more about when we were talking earlier? You were saying that you think of chemistry as learning a new language. Maybe you can talk about what you meant by that.
So what I meant by that was that when I think of learning a new language, which I'm not all that great at, but you can't just pop it back as if you've memorized something. You know, you have to feel it. You have to understand it inside. You have to be able to visualize it. So when you say cat or dog in another language, you can't just splurt. It has to, if you know the language, it has to be in your brain, cat, and automatically the word comes out for that language. And so for me, chemistry really is a language because it teaches you, you not only learn the words, but you start to visualize things around you in different ways. And so in that respect, I see it as a language. And when students talk to me about, undergraduates talk to me how difficult organic chemistry is, I tell them that organic chemistry is, at first, it's a language because you have to study it like a language. You know, they're thinking, how can I possibly pass this exam? And I say, well, you don't wait until 2 weeks after the class to start learning whether it's hexane, heptane, or octane. You have to learn it all the way, every day, like you do a language, because otherwise you'll never learn it and you'll never really appreciate it to a certain depth. And I feel the same way about chemistry, in that you've got to just keep up with it until it makes sense, and then you can speak it and visualize it and speak it at the same time.
So after corrosion, I mean, we have, this was taking place at Bryn Mawr. And then what took you out to Oregon?
So I loved my time at Bryn Mawr. I had great students that were there, but it was a combination of both teaching and research. But I realized that the research was a lot more important to me than the teaching, which I didn't anticipate after graduate school, because I didn't take a postdoc. I went straight from graduate school to Bryn Mawr. And then I had some great ideas of what to do to make a research program. And so then Steve, my husband, was at Bell Laboratories. And so we both decided that it was, we might consider a move. And so we looked around and had some offers and decided Oregon was the best for us. And so because of its interdisciplinary nature of the science. And so I went and expanded my research program, started out doing the electrochemistry-oriented work with lasers, and then went on to, a few years later, to be studying liquid surfaces, but always with fancy laser systems.
Okay, and explain what it is. I was, again, reading this notion of the interface, the space, the connection between water and whatever's on top of it or whatever it's on top of. Why is it important to know about that?
Well, if we're talking about something like let's say an air-water interface, your glass of water here, I look at the surface as really the doorway to anything getting into that water, whether it be carbon dioxide in the air or whatever. But there is this high surface tension, right? Things sit on top of water, leaves and bugs. And so the very surface layer is a bit of a door in order for things to get inside. But what makes that top layer any different than 10 or 15 molecules down or 5 molecules down? There's something got to be really special about that top layer. And if that top layer is the doorway and you're trying to look at how different pollutants or atmospheric processes happen, we want to know whether they just bounce off or whether they actually stop and absorb a while or go in, because it really controls the reactivity of most of the chemistry that goes on inside of here. And so we want to be able to understand what's happening on the top to better understand what happens when they go in and react.
So are there ways of changing the surface tension of the water so that things can get in more easily?
Yes. Yes. You put, in fact, a lot of different molecules can go on top. And the most common is a soap, because that's how soaps work in breaking down that surface tension on water. And then it makes it easier for everything to go in.
Yeah, so these are called surfactants, is that right? Huh. And so will you see a different signal with your laser analysis of the nature of the interface when you have water with a surfactant on top of it versus water without a surfactant on top of it?
Big time changes.
Right.
Big time changes.
And so would you be using that knowledge to make different surfactants or better surfactants, or just to understand what surfactants do?
So in the surfactant industry, we have surfactants in your toothpaste, in your shampoo, and different formulations.
Why?
Well,
okay.
They figured out why, but the why is by just trying different stuff. So what's not really understood is what kind of molecular structure makes a surfactant do a certain thing. So you can't say, I want Joe to use toothpaste that's really good, so let's put in a sulfonate in his toothpaste to make it work well, because we know the molecular properties of that sulfonate do this and that when it comes to water. We don't know that. It's hard to know that, and that's what we study. So there's more predictability as to what molecule will give you what function. So we don't make the surfactants to make the function, but we try to understand what the structure needs to be in order to have, for example, to make the surface tension a lot different.
So why, I mean, but I'm just curious, what property of toothpaste would be enhanced by a surfactant?
Oh, being able to scrub gunk off your teeth.
I see. So you're studying the gunk water interface.
Well, in many respects, that's the other side of the research, which is the oil-water interface.
Yeah.
Because you're trying to break that junction between oil and water.
Break the junction?
Yeah.
Why?
Because you want to be able to break the oil up. So you want to be able to, I mean, that's how an oil dispersant works in an oil spill, is to be able to put a surfactant there and get the oil to break up into smaller particles, these tiny droplets, where water is surrounding a tiny oil droplet that's stabilized by this surfactant so that it can wash away or bugs can eat it or whatever.
So that's,
And that's how your laundry detergent works too.
Yeah. I got into this a little bit by talking about the surfactant in the lung that is allowing your alveoli to expand without making each breath a challenge. But that's more of a physical phenomenon, huh? So tell us about receiving the Priestley Medal. How do you win one of those?
I don't know. You pay off a lot of people.
I figured. How much does one of those go for now? I mean, seriously, when did your work begin to get recognized as something that was deserving of these top honors? Because, I mean, I don't think if I were to go out and ask 10 people on the street whether someone who studies the water-oil interface at the molecular level was the most important chemistry work in the world, they probably wouldn't. It's not like
It's curing cancer.
I mean, yeah, right. It's not curing cancer. So when does it become recognizable, and how recognizable should it be? When did your work start to get attention?
I would say probably our 2001 Science article was the one that brought the most attention to it. And that article was saying that normally in the past, people have thought when you put water next to oil that that actually water would ball up in itself and wouldn't want to have anything to do with oil. That's a lot of the biological texts. And yet theoretical work said that when water is next to oil, you're going to have a big vacuum. You're going to have a vacuum layer. Not huge, but a vacuum layer. And what our work showed actually was when you have water molecules next to oil, that they actually straddle the junction between the oil and the water, and they bond to the oil, weakly bond to the oil. And that sets up really interesting properties at an oil-water interface that wasn't really expected to be able to see that bonding with the oil.
So where does that go from chemistry to physics?
Oh, it's a combination of chemistry and physics.
Okay.
Because it was a combination. We started doing theoretical work along with the experimental work, so it brought it all together.
So when we were talking about your activities with encouraging women, and we were saying at the start that you don't have all the voices in the room. I guess having heard you talk about all this stuff, I'm not sure that I understand where gender comes into it. I mean, why would a woman versus a man be able better to imagine the oil-water interface or the experiment that would reveal certain interesting properties of the oil-water interface?
Oh, I don't think I don't think that I would ever come to that conclusion that a woman could come up with the solution better than a man. I just think that we need to make sure that when we have an ensemble of scientists, that we make sure that we've got everybody's voice in there.
So again, I mean, there's a social good and there's a scientific good, and,
yeah.
but you're saying they go together.
I think they do go together.
And so this coach, talk a little bit more about that.
So in the 90s, late 90s, I was noticing in chemistry that there were a lot of I was kind of mid-career, full professor at that point, but I was noticing that there were a lot of, that was a time where people were getting awards and accolades for what they were doing, and invited talks and offers to go to another university, and there were very few women that were getting acknowledged in that way, even though they were doing as well as the men were doing in terms of publications and so forth, but they just weren't getting the recognition. And so I got a group of a dozen senior women chemists from around the country, and we got the Dreyfus Foundation gave us some money to start talking about what the challenges that we were facing and what we might do about it. And so we got together the first time, and everyone was saying, oh, no problem for me, it's perfectly fine, and it's okay. And so, but they did see some issues. So then it was a busy group of women, and so the next meeting, we were funded for 4 meetings. The second meeting, everybody was busy. We all had small children and everything else. And first of all, the first meeting, most of the women had never been in a room full of other women scientists before, even chemists, so this was unusual. But the second meeting then, we brought in a team of a couple of women that were not scientists, but they were good at teaching professional skills development. So they did a workshop for us on negotiation. And in this negotiation, we were supposed to describe the challenges that we had that a negotiation might help with. And then all the stories came out. One woman was losing her lab space, even though she had everything was going great. Another woman was being denied for this particular promotion. All these stories came coming out, so we realized we were all in denial in the first meeting. And so they gave us, we worked through these problems with them, and when we came back 6 months later, everyone's lives had changed. The woman got her space back. Just everyone's lives had changed. And so I said, wow, this is pretty cool. So we need to start offering these to other women scientists.
What happened at that meeting that empowered the women to reverse some of the negative things? What changed?
To taking control.
Okay.
It's all about taking control of your career, rather than assuming that someone else will take care of you. It's all about taking control. And it's not just for women either. I mean, it's for everyone. It's everyone but enabling, taking control while also working within the system to make it work. So a lot of really good advice. So we then got funding from NSF, NIH, and Department of Energy, and then have other workshops on leadership and communication, and so we then started offering them all over the country, and at professional meetings. We've done them here at Lawrence Berkeley National Labs, and then and we continue to have an advisory board that has grown, and now it's not just chemistry, it's across all the different engineering and science disciplines. And that's where all these women have come to.
So give me a report card. How are we doing in 2018?
Well, we just did a survey, and in chemistry, not much improvement in the last 10 years in terms of climate in departments. Numbers are going up slowly, and chemistry is one of the better players relative to some of the other disciplines. So we're still have challenges ahead, and we're better at the undergraduate level and even graduate student level, but it's really getting women into leadership roles where the real challenge continues.
So is this, I mean, I have a friend who's a department chair at Hopkins, and she's pointed out to me that you see the drop-off most precipitously when you go from associate to full professor. It's at this very highest level. So without holding up a mirror to myself, what would you say is the biggest barrier to this? I mean, what's happening? I mean, the NSF is saying it, the NIH is saying it, the Department of Energy is saying it, the foundations are saying it, the society is saying it. It's not happening. That this has to change. What has to change to have to make this change?
Well, I think that now a focus on the issues of implicit bias and how we all have biases, making people more aware of that. But I think even more important is that leadership at our institutions certainly have to be driving and monitoring, and that means collecting data on progress and watching to see that you're making progress. But I also worry a lot about the trenches. So I worry a lot about what happens in the department, in the faculty member's laboratory, where you can have weird things that go on that don't get reported because of fear of getting reported, because it may ruin your career.
Mm-hmm.
And so I worry about that level, but I also worry about the fact that that women oftentimes, that there's biases against them reaching leadership positions, but women have to also work harder to accept leadership positions if they so feel that they can do it.
So it must be, I mean, I'm just thinking, and I would like to invite the audience to ask questions, but I'll let you think about one while I ask this or make this last observation and wonder what you think about it. But it must feel a little galling to be told that America needs to be great again when it was at a time that you're trying to move away from. I mean, to look back and say, make America great again, sounds like it once was perfect and now it's flawed and we want to go back, but everything we've talked about says it was flawed in the past and we want to go forward. So how does that make you feel?
Well, I haven't thought about that. You know, great is in the mind of the beholder.
Mm-hmm.
And some people really thought, you know, if I'm thinking about sciences, some people really thought that science 20 or 30 years ago, there were all these, or even 40, 50 years ago, there was all these things undiscovered. So that was really the heyday of science. But so great is in the eye of the beholder.
Okay.
So, would you like to take some questions?
Sure.
Let me get where I can see people. So, would we have a couple of mics here? So, people would like to come up with some questions. Wave a hand so we can. It's not that shy in retiring a group. So.
Apparently so.
Yeah.
No. Oh, good.
So in speaking with some of my female colleagues, we were discussing the fact that this event is taking place within the realm of a Women in Science series rather than a People in Science series. How do you see the role of series or awards or other things dedicated to women in science specifically?
Well, I think that's a really good question. And as Joe and I talked about before, when can you quit doing that as opposed to just having regular awards in science? But I've seen the impact that giving more visibility to women can have, especially at the early stages of their careers, where you're just trying to build up your CV in any way that you possibly can. So let's just celebrate the fact that there are awards out there at all. Someday we hope to be able to not have to celebrate women in science or African Americans in science, but we're not there yet. So let's celebrate. You know, the more parties you can have, the more celebrations, the better. I believe. That's a good question.
Other question?
Hey, Deb.
Thanks for coming. So I guess I'm curious. So what impact on your career has there been for doing coach? Has it been a positive or a negative?
Well, it's interesting because in the early days of starting coach, I was told not to. Was advised not to because it would look as if I wasn't so serious about my science. And but I just couldn't. I just couldn't. I mean, I can't. Science is wonderful and doing science is wonderful, but I need something else too. And our experiments are really, really, really hard. And so I tell people that I have the option of either constantly haranguing my students to make the results come faster, or I can go do something else for a while and check back in with them and keep my stress level lower. But overall, it was wonderful winning the National Medal of Science, where it was acknowledged that I was winning both for my science as well as for our activities on women in science. And so that was really gratifying because it showed a recognition that both can be important. And I think that's the strong message that we want to give to our younger scientists and everyone else, that it's okay to do your science and something else too, because maybe your life will be richer that way. On the other hand, just doing science is rich too, but personalize it in some way.
I'll take one question myself. And for a chemistry department, and you know quite a few of, do the women who are faculty members have more female graduate students than the men in the department? Just on exploring. Is that your experience?
In my department?
Yeah.
No, I wouldn't say so, actually. I'd say, no.
Okay.
No, I wouldn't say so.
Okay.
You know, I have to say, though, to finish up with that, is that whenever I've had a group that was a little too male, then too much stuff got broken. But when it's too many women, not enough stuff gets broken.
I won't follow up on that. Go ahead.
Was there a point when you realized you had to readjust your expectations for yourself and realize that they were hindered by what others expected from you and that you were capable of going beyond that? Or was it realizing that others' expectations of you were scaled below what you thought you were capable of? Or did you ever have an experience like that?
Let's see, where I had to adjust that their do it again.
That you realized that your expectations for yourself were hindered by what others, like male scientists, thought you were capable of, and you had to personally realize that there was more you
No,
could
this
do.
was all me. There was a point where I realized that actually I was better than I thought I was.
Yeah.
And that was more the turnaround. That was more the turnaround. And I don't think it was based at all on what other people thought as much as, and maybe you can say, well, you know, whatever I internalized had some social influence to it too. But once, that was a phase transition, yeah.
So I have one more issue about another issue of implicit bias, theoretical and experimental. In physicists, you know, the theoretical physicists are considered smarter than experimental physicists. So physicists do experiments so theoretical physicists can win Nobel Prizes. How does this go in chemistry?
This is why you do both.
It's very interesting, though.
Can't get her to take that one on.
But it's interesting you say about expectations. I think that question is interesting because I've seen at NPR, they've asked us to self-evaluate. You know, we write these evaluations, and I routinely write, greatest science reporter known to humanity. And it's partly because I believe that, but partly just because you ask me my opinion of me, it's going to be good. And I talk to a lot of my female colleagues, and they're being far more honest. Oh, I have flaws here, flaws there, and I'm going, yeah, but that's not this exercise is being, you're supposed to be a star in this self-evaluation world, or why, you know, if somebody else doesn't think you're doing a good job, fine, but if you don't think you're doing a good job, that's not good. So I feel that I've known women that are far more competent than I am, but they don't seem to know it.
Right.
And I wish there was a way. And now that I'm working with a young woman who is far more competent than I am, I hate her. But I'm trying to deal with it.
Okay, Susan.
Yeah, I wanted to make a comment, and then I had a scientific question. The comment was, what I found scientifically is that when you work with people from different fields and different areas, it's like a symphony of ideas. And they build on each other, and it's like a Picasso where you have all these viewpoints that you try to assemble into a scientific idea. It's probably as scrambled as a Picasso, but you try to do that. I think that's what women also bring, or you know, underrepresented minorities. They bring in instruments that are rich and can add. And the question I had was a very simplistic question, and I was curious, what's the difference between an air-water interface and an oil-water interface?
Ah, good question. Yeah. The oil-water interface, it's just it's similar in some respects, except you've still got that oil layer that's bonding to weakly to the water. And so the properties of that interface is different because you actually set up a bit of a field to draw things in. And so it's different from a very molecular level, but in some respects similar. It's just you've got the suppression of the oil that is there. But soaps still act in similar ways.
Okay, got one over here.
To Mike's previous question about whether theoretical or experimental, Geri's response is spot on. This is why we do both, right? To have multiple perspectives there. And as somebody who very much enjoyed your summer undergrad program back in '94, the amazing thing about that setup compared to where I'd been before was that the chemistry and the physics was all mixed up. Yeah. There were very few barriers between things.
Great.
Thank you.
Okay, Heather. Here's a got a few. Go ahead.
Hi. Thanks for the talk. I work with the undergrads who come here to do internships at the lab, and I was happy to hear that endorsement about undergraduate research at the beginning. And I'm just wondering, for our undergrads, we really encourage them to develop professional relationships with mentors, researchers who know more than them. And I'm wondering if you could just speak about the role mentoring has had in your professional career, certainly beyond your undergrad days.
So I would have to say that I don't really know that I had that much of a, we had another question over here. I want to get the mic there. Yeah. I don't know that I really had what you would call a long-term mentor, but I had a lot of coaches and I had a lot of sponsors. And so they've had a huge impact. And so you can have a mentor that's short-term coach. You can have someone that is out there as a cheerleader for you. And I've had both of those, but not so much a long-term. And how do you fold friendships into that? Wonderful friendships of other scientists over the years have been valuable too.
Okay.
Thanks.
I think we have two people holding mics, and I think we'll get to both of them, and that'll probably be at the end. So first here and then there.
So you talked about how, like, even in the undergrad classes, you had less women, let's say, in calculus and the similar classes. So do you think there is a way to encourage women at a younger age, because you say that at associate level, between associate level professorship to full professorship, you see a drop. But I also see that there is also low interest at the beginning.
Yes.
So what is your comment on that? How can we, increase the interest of, young women and maybe unrepresented minorities to get involved? Is there something they get in the lower when they're younger where they don't feel as interested in science and technology, or what's your comment?
Yeah, so I can't really speak so much through the K through 12 level. I think the sooner you can get any student hands-on experience and get involved in even undergraduate research, our retention rate for underrepresented groups is just abysmal. And so we have to work on that retention rate for them, more so than our majority groups. And I do believe that by getting involved in undergraduate research as soon as possible, you then have, if you're in a good group, you have a good mentor, you have graduate students around you, or if you're even at an undergraduate institution, getting some hands-on is really, really important. And feeling like you're part of something, I think, is really important. And for me, that's what saved me, was to get me in a kind of a family environment like many of our research groups can be, that are showing you where you're going to go after next year and the next year and the next year. Because, if you're from a background like mine, you have no idea what's going to happen next year or the next year or the next year. And so having people around me that showed me what I would be doing if I stayed on this pathway made a huge difference, because there was no reason for me to gone on this pathway if I hadn't had that experience of people around me.
Okay, and we'll have our final question.
Okay, so kind of going off of what you said, that when you were a child, or like even now, you feel as a man that you can say you are great, you are amazing, but when you talk to female coworkers or anyone, they more point out their flaws. But I think that's something that comes from when you are young, that as a boy, or at least when I was a kid, seeing the boys, they were constantly encouraged, like, you can do it, you're great. And as a girl, you were constantly said that, no, this isn't what you can't do. You're not good enough, you're not strong enough, you're not smart enough, you're too colored. I don't know if that's something that you've ever considered, or if Coach or any of the programs that you've been experienced or participated in reaches out to kids, as what was said before, that going towards the younger children, bringing them into the field or their interest, telling them that they can do it, not just boys versus girls, but anyone, that they can do it. What are your comments on that?
Well, I think that's critically important, and I think parents play a huge role in that. I mean, if it weren't for my mother, who was encouraged me, she showed me she could do math, arithmetic faster than I could. She taught me my first chemistry lesson in the beauty shop. She would bring out bottles of hair dye, and she would point out which elements on the periodic table were on that hair dye. I mean, those kind of things stuck with me and kept me going. So I think parents have a huge role to play in that. And then it was my 8th grade math teacher. I wouldn't be here if it weren't for my 8th grade math teacher, Mr. Smallsreed, who pulled me out of the class and had me do a geometry problem on the board and said it was in a way he'd never seen it before. Very creative. Now start to tear up. And that made a huge difference because my counselor had told me a few days before that because I was good at taking math exams and could write fast, I should be a secretary. So, the fact that I had this one teacher that said, no, you should go into math, made a huge difference. Otherwise, I'd still be doing shorthand and bookkeeping and everything else. Thanks for asking that question.
Okay, I think that's probably the right place to end up. So I would like to thank both Geri and Joe.
Great, thank you.
Okay, and I would also like to thank all the people who asked great questions and look forward to getting together and doing this again in 6 months or so.
Great, thank you. Thank you.